Okay. And so what we're going to do today is we're going to talk about one of my favorite riddles in all of mathematics, the pirate game. How do we divide the spoils? And so if you have seen this before, be silent in the beginning stages. Okay. So the way it works is, as we said last time, we have 5 pirates with the boring names of 1, 2, 3, 4, 5. The lowest named pirate always has to propose a way to divide the 100 gold coins. If a majority or more vote for it, so 50% or more, then the plan passes and they divide the money and the game is over. If, however, they can't get at least 50% in favor, then that pirate who proposed is killed, and the next lowest named pirate now makes a proposal. You repeat until a plan is accepted. We will assume the pirates are intelligent. So before we started today, we were having a conversation about how you have to, in some school districts, talk about it's okay if the pirates are not fair. It's okay if not everybody gets the same amount of money. These are pirates. Pirates are not a protected class. They can have negative characteristics, but they will be at least intelligent pirates. So they will be very smart. And smart can mean different things to different people. So does anybody want to talk a little bit about how you might try to analyze this? And I did flash a hint for about 1 billionth of a second. Any thoughts as to how you would attack something like this? And then just to remind us where we were, we talked last time about what does it mean to vote, and that's why vote has been circled. And so the way they're going to vote is they will discuss, and then there will be a call to question, and then everybody will write on a piece of paper, yes or no. And everybody amazingly has the same handwriting. And they'll be put in a basket, and then they will be pulled out, so you will not know which pirate voted for which. Now, if everybody says, I'm supporting the plan, and it comes out 4 against, 1 in favor, okay, you can figure out then how some people voted, but you will not know the names of who voted which. Everybody votes at the same time, you vote anonymously. So anybody have any thoughts as to how you would attack this?
I started by just thinking, if I'm pirate 1, how many votes do I need?
Okay, good. So the first one is, if I'm pirate 1, if I want to live, I need to get how many votes?
2 more votes.
2 more votes. Did other people think about it this way?
Yes. I feel like almost the other end. Like, it's like if I'm pirate 4,
right,
and it's just me and 5, like I can make any plan I want because I have 50%.
Almost perfect. So don't think about if you're pirate 4. What should you think about?
If you're pirate 4.
Right. So a lot of times the problem we're given is not the first problem we should solve. We should start with something easier. If I'm pirate 5, what happens? I get all the money, right? We said intelligence, so I'm not going to vote against my plan. So I almost think it's easier to start backwards. What if we only had 1 pirate? What would happen? What if we had 2 pirates, and pirates 4 and 5? What would happen? And analyze it going backwards, rather than starting off with 5 pirates and the problem that was assigned. So just a couple of comments. Is the gameplay clear? Can it be interpreted more than one way? With college students, it's probably clear. With elementary and middle school students, I would not be surprised if people are looking at things differently. And in one of the games we're going to play later today, and if you do a good job, you get a candy bar. The kids have historically had a lot of trouble playing it. They make a lot of mistakes. I at least now know which mistakes they are and can do things to minimize that. But you really want to make sure everything is clear. Can you interpret things in more than one way? I talked last time about how my department gives an award for best colloquium attendance for seniors. And then we started to allow 5 talks to be counted as a junior. Does that count towards the prize? If we split 50-50, of course it counts. Of course it doesn't. How should you try to analyze the game? So there were 2 very natural schools. Start with pirate 1 and just think, what do I need? Or imagine there's only 1 pirate, pirate 5. Have you seen anything like this before? This is just general advice in life. Whenever you're given something, can you relate this to something you've seen? And then the next point is just, is there anything special about 5 and 100? In some problems, these numbers are often very carefully chosen so that they use key properties or whatnot. Sometimes they're completely irrelevant. it doesn't really matter that it's 5 or 100 in this problem. It could, and there are other problems where those numbers do matter. But always ask, is there something special about this? Am I being pushed in a certain way? I have one problem, which is one of the best exam questions I ever made, where the numbers are deliberately designed to confuse you. And the students get the answer, and they get a really bad answer, which is what I want them to get. And then I was the one who proposed the problem, and I didn't realize when I proposed it, oh my God, there's an answer that's 1,000 times better. That's much easier to do. And if there's interest, I'll show that later. The numbers can blind you into looking in a certain way. Okay, so just fixing the slide. If otherwise. Okay, so we're assuming the pirates are intelligent. So we play a smaller game and work up. So if we only have one pirate, so they get all. Does everybody agree the one pirate game is trivial? So this is a good place to remark. Should we have started with the lowest numbered pirate proposes, or should it have been the highest numbered pirate proposes? Which would be easier? Because I know you did your shortest, and it might be easier to start with the highest number as we're starting to analyze these things as we start adding, because then it would extend better.
Kids understand better. So just one. Now if there's two.
Right.
Now
and so this is probably a bad way to do it. And so we should probably do it the other way. We should probably start off with the highest numbered pirate proposes. So if it's just pirate 1, now pirates 1 and 2. And you keep adding like that. Okay. So now let's say we have pirates 4 and 5. What happens?
4 gets
So 4 proposes. 4 gets 100. 5 gets 0.
If 5 votes no, it doesn't work. No.
No, because you only need 50%. So passes, right? Okay, what if there are pirates 3, 4, and 5? Do you all agree that this is the first time that it might actually be interesting and worth shopping here? What does 3 propose?
There is to convince 5, right? I think. But
Well, let's be very careful. What does 3 have to do?
get one other person.
3 has to get one other person. They don't care which.
I thought 3 should take 99 and just offer 5 1.
Okay, so this is one possibility. 99, 0, 1.
What's 3's goal? The survival or not?
Oh.
Because if they do that, why
It's
wouldn't 5 say no?
Because if 3 walks the plank
So,
and 4's gonna.
so what happens if this plan fails?
Then 4 gets it all.
Yeah.
So,
And 5 gets
so if fails, 3 dies, 4 gets all.
I guess 1 doesn't seem like it's as enticing. It's just 1.
It's better than 0. And
Yeah, it is.
just 5.
Right.
5 operates on that logic. Like 1 is better than 0.
I'm
Not
Or
like
emotionally,
yeah.
My students try to be fair and they were like, well, because we do it at 500, they would always go, well, at least 200, 200, 100, and I'd be like.
so what do you think?
It's very intelligent.
They're intelligent. And so if
5 goes with it.
so is Pirate 4 gonna support this?
No.
No. Pirate, right, and exactly. Pirate 3 doesn't care. Pirate 1 will Pirate 3 will definitely support this. And Pirate 5, support or not support?
I think so. Yeah.
Because then Marie gets that.
Because if it fails, they get nothing. And so then by that logic, if we have pirates 2, 3, 4, 5, what would be the proposal?
There's no scenario where 5 dies.
Right.
Correct. Because they're intelligent. And so if it gets to 5, 5 votes for
Yeah.
5 is not going to die.
I guess I'm hung up with one coin is worth not as much as 3 twice.
Right.
And so 5 has negotiating, like that person could just sit there and say, all right, if you don't, I'll put 0 and you'll die. So you need to give me more
So
than
you were
1.
getting to that point earlier than I wanted. We can do it now. No, this is where it gets interesting. Because, so,
Like 3 needs to buy your vote.
so let's hold off on that for a second. We'll continue the classic analysis and then we'll get to that point. So in the classic analysis, what would be the proposal now with pirates 2, 3, 4, 5? What would pirate 2 propose? They just need to get 1 more vote. So they could get 5 2 coins.
Yeah.
And if they do that, they would definitely get 5's vote. Because 5 knows if I don't support this, then we're going to go to a case when I only get 1.
Yeah.
Could they do better than that?
1 coin of.
1 point to 4. Because if they give 1 coin to 4, 4 knows that if I don't support them, I get nothing. So I think what they would do is they would actually give 1 coin to 4. And then if we had pirates 1, 2, 3, 4, 5, what would the proposal be?
Can we go back to the second, the 2, 3, 4, 5?
Sure.
So when I thought about it, I thought 4 would vote no for that.
Well, but if 4 votes no for this, then they go to the case of pirates 3, 4, 5. And if it's
Right.
3, 4, 5, 4 gets nothing.
Right, okay.
So pirate 4 is not thrilled that they're only getting 1, but they realize that if they don't support this, they're going to get nothing in the next round.
Right.
So they have to support it.
Right.
And now if we have 5 pirates, what does pirate 1 propose? They need, as you said, 2 votes in addition to their own. Who can they get and how cheaply?
3 and 5.
3 and 5, how much? Yeah, 1 to each. And so, do you notice any alliances forming?
3.
3 and 5, odds and evens. So there's an odds and even split. So there's a lot of problems that fall like this. Okay. Now let's get to the very interesting proposal that was made, and this depends on how much stones you have. So here is the 3, 4, 5, 99, 0, 1. And now, James, give me a counteroffer.
I just think that
No, I don't want you to think I want a counteroffer.
I would flip it.
Okay, good. So you're going to the opposite extreme.
Or take it all.
Well, that's what I was wondering.
Yeah.
So you're gonna do 99 or you're gonna do 1 for me? I'm sorry, are you gonna do 1 for me or 0 for me?
I like that one better. Okay.
Yeah, but you have to vote.
So what James is saying is pirate 5 is James is telling pirate 3, your proposal that I get 1 and you get 99, no. I'd like all of it. And if you give me all of it, I'll let you live. How much is your life worth? So
Here's the thing what I was struggling with. If these pirates are all intelligent and
Yes.
can figure this all out,
yes,
then it just all goes away. Because then you're like, okay, so if we come to this determination that there's this set solution,
right.
and then everyone knows that, this is like literally keeping me awake.
Right.
So then if 1 knows, let's just say that 3 gets everything, then 1 could say, actually, I'm gonna take 98 and I'm gonna give 2 and 4, 1 each.
Well, let's go to the case where we're not going to have anybody playing chicken. Okay? Is that the case you're in where no one's playing chicken? Because you're talking about intelligent. And so it's just Are they valuing your life as well? So do it by how many pirates there are. If there's only one pirate, the pirate gets everything. If there's two pirates, pirate 4 gets everything, pirate 5 gets nothing. So pirate 3 is making their proposal. Pirate 4 knows if the proposal fails, I get everything. Pirate 4 is not going to support any proposal from 3. Right? So pirate 3 knows that if their proposal fails, they're killed and 4 gets everything. That means 5 has a natural incentive to support 3. The question is, how much can you extract from that? Here's my counter offer to you. It's being recorded, so I will not use the language in which I would make this counter offer as a pirate. But there would be some strong language here. Here's my counter offer.
4 wouldn't support you because Collins and all.
4 would support me, absolutely. Absolutely 4 would publicly support me. I can definitely count on the public support of 4 for this proposal. Right up until we go to the secret ballot, where 4 writes no, and I'm killed. So this would depend on how we vote.
But if your pirates just would 4 even lie if they're voting for you?
Are we pirates and you're asking about qualms about lying?
Well, so then would they care if it's secret ballot or not? Or they could just be like, no, I want it all. Like, what's the harm before just being honest about it?
Well, if everybody has to hold up their hand and you can still adjust your vote while the hands are up. Does everybody agree? You know, if you do something like that, if
It
you
doesn't hurt 4 to just stay with no. Like, if they lose, they lose, but if they win, then like, worst case scenario, they get.
but see, 4 doesn't want 3 to pivot back to giving something to 5.
Yeah.
4 needs 3 to be lulled into a false sense of confidence. So if you could basically say, I'm locking in my vote as a yes. And so long as everybody doesn't change their vote, my vote is going to be locked in. We all agree to lock in our votes. If you do some kind of voting like that, where is everybody comfortable locking this in? And if everybody says yes, then it's locked in. If you do voting like that, then this is a legitimate proposal. And this is one of the reasons why I am strongly supporting public votes not be in public, but with clickers, because there's a lot of pressure for people in towns on budgets and whatnot to vote certain ways. So with our voting scheme, 9910 is not going to fly because I don't trust. And you would just laugh at me if I came back with that. Go ahead, Steve, make that proposal. So there's several ways I can come back to you. So you're giving me nothing. And I could do the following. 50, 0, 50.
So we're saying that they're not 50. If I know that I'm getting 100.
But you pirate 5. If this fails, pirate 4 will get everything. You know you get nothing if this fails. You can still try to, you can come back and offer me 0 again. And we can see who blinks first.
Yeah.
You know, because my life is on the line. If the vote goes against me, I'm dead. But you get nothing.
Right.
And so would you accept, and again, it's tough because this is hypothetical.
Like me, yeah. Like that's great. I'm getting half. But if I'm putting my pirate hat on, I would probably try to. I would squeeze every coin out of them, and so.
But if you squeeze too much, you're going to get nothing.
Yeah.
If you squeeze too much, I walk away.
I wonder if there was like if it was like, oh, you end up with 0 coins, you also want. Like, how would that change the game?
We changed it tremendously.
Yeah.
So, I mean, it would be great to consider stuff like that.
Yeah.
That's more than how we do it.
That if you have no coins, you die.
You die.
And so then,
Because then like 4 is a player again.
correct. And then you can try to win them. But again, if they vote in secret, then 4 could pretend to be supporting your plan and vote against it. And so the question is, I strongly support you trying to get as much as you can out of me. would you hold the line? I was very reasonable with my counter offer. I went straight to 50-50. I didn't try to go to 66-34. I went to split, let's just split it.
I think 5 would want more. 5 came back with, I'll take 100, you'll get 0.
And what I'm saying is,
they don't seem reasonable, I guess is what I would.
and what I'm saying is, you want 100, I was gonna give you 1, let's split the difference.
Is there even the ability for them to be negotiating, or is it?
So again, it depends on how you play the game. I think it's more interesting if you allow them to negotiate and say, we can have a discussion before the question is called. So I have not made a proposal yet, I'm just discussing it with you. What would you like to do? There's no right answer here. It depends on the mathematics to some level, but then it depends on the psychology as to, are you willing to bluff? Are you willing to gamble? Are you willing to risk? Are you willing to say, I'm willing to die? I'm not willing to give you more than 50. If you came back with, and I'm not saying you would, what if you came back with that? We're now talking about 1 coin. Or I could have come back instead of 50-0-50, I could have come back with 51-0-49. I could have said, I'm taking a lead. Since you gave me nothing, I would have split it equally, but you gave me nothing. I was willing to give you at least 1 coin. I'm going to take 1 extra. You could make the game a little bit more interesting. Instead of having 100 coins, how many should you have? 101. Because now, depending on how many you have, it's going to change things a little bit here into here's an extra coin, and someone's going to get the extra.
Well, it's funny too, because in the first, if 5 rejected 1 coin,
Right.
then they don't see 1 coin as being very significant.
Right.
So the difference between 50 and 51, in theory, is not that big, but it's like, at that point, it's an emotional.
It
response.
is absolutely an emotional response. And so when you think about how nations interact, when you think about stuff like that, this becomes extremely important. And so a lot of times it's whether or not the bluff is credible, whether or not people are willing to take the risk or not. And depending on who you play with, you can get very different answers. So it'd be fascinating to have students in classes play this. Now the problem is if you're just playing for fun, if you're not playing for anything real, then it's very different to say, I'm going to get nothing versus, do you want the folders? Need the folders? Okay, perfect. So yeah, so there's a lot of stuff you can do here in terms of using this in the class. I love the idea of going backwards. I love the idea of just thinking about what's the best notation to use. How do we want to name the pirates? It's more fun when the kids can choose the names, but it can be a little bit confusing as to who's making the proposal. People often choose names based on A, B, C, D, so it's easy to follow. Doing it with 5 pirates and the lowest named proposing is stupid. I should not do this. It's terrible. It should be the highest named pirate is the one proposing, and then it more naturally reduces to something you've previously seen. But depending on the assumptions you make, and this is a great thing to talk to kids about, what happens when you try to use math in the real world? When you are negotiating with people, a lot of the negotiations depend on how much you can make people feel that you value something versus how much you actually value something. And so, I'll just pause it briefly.
So there's no way.
Okay. Technical malfunction has been fixed. So if there's bluffing, what would happen with 1, 2, 3, 4, and 5? So this gets really interesting. Before we do 1, 2, 3, 4, 5, let's just do 2, 3, 4, 5. So we now know we have 2, 3, 4, and 5. There is definitely an alliance between 3 and 5. 2 just needs 1 more vote. It's going to be hard for them to swing 3. What do you think 2 might propose?
I thought two would propose, but I think I was thinking
In the
it's
old
not including like emotion.
Right, right.
I was just looking at
Yeah,
strategy.
yeah.
I gave three, all of them, 100. Because I thought then, otherwise, three could vote no. And then the next round, three could give themselves 99 and 5 won. And so I thought the only way to ensure
Right.
that three would vote with you would be to give three all 100.
So
And then you were guaranteed they'd say yes, because that was be three's only way to get a 100.
So if you do this, I think you would definitely get three's vote and you would live. So I like that solution. You get nothing, but you do guarantee.
But I wasn't
that.
thinking about the humanity of it. I was just thinking about how do you guarantee that that person votes
Yeah.
with you.
Usually, thinking about the community is not the #1 item on Pirates' to-do list. So this would definitely, I think, pass. But it's probably not the best Pirate 2 can do. Because Pirate 2 knows that if their proposal fails, Pirate 4 gets screwed. So what could Pirate 2 propose? No, but it's a good solution. And again, one of the things that's nice is when math doesn't have just one solution. What could Pirate 2 propose?
It's the same predicament they could give for 1 coin.
So they could do the 1 coin, and then Pirate 4 could say, hey, wait a minute, I remember what Pirate 5 was saying. So what do you think they might propose?
50-50.
So they might do 50-50. And again, Pirate 4 can try to convince Pirate 2 to give them more. But this does seem like a pretty fair distribution between Pirates 2 and 4. Hey, look, if we don't come to an agreement, we get nothing. Pirate 4 can always say, I want a little bit more because otherwise you die. Are you saying your life is worth nothing? And so they could probably convince Pirate 2 to go up a little bit, but roughly 50-50, I think is a reasonable thing to come to. Now imagine we have 5 Pirates. Do we all agree that certain Pirates are going to get screwed by Pirate 1's proposal?
Yeah. I think 2 and 4. Probably.
Do you agree? Do we agree or not?
Right? Because they're about to get.
Just remember, like Pirates, I don't have to be a nice person. I don't have to be a kind person. I don't have to be leading you in the right direction. Do you think Pirates 2 and 4 are going to be screwed by Pirate 1?
It's possible. I think unless Pirate 1 was like, oh, I'll give like 51 to Pirate 2 and then 49 to Pirate 4, because I can. The Pirate 4 could say no, you know.
All right, so people are comfortable that we're going to screw Pirates 2 and 4? Okay. It's mathematically comfortable.
Yeah.
You know, this. So what will Pirate 1 propose?
50-50 or 35.
So Pirate 1 gets nothing?
Yeah, for that's what.
Yeah, like they're dead, like unless they get these 2 votes.
But they can say, look, if you don't pass my plan, Pirate 2 proposes, and 3 and 5, you get nothing.
Right.
So 3 and 5 can both say, you're gonna die, and Pirate 1 can say, and you'll be broke.
$34, $33, $33. Yeah. Whatever. If I'm willing to risk my life, I guess I'm also
Right, so
willing to take one more.
so it comes down to who gets the extra one. Pirates 3 and 5, I don't want you fighting amongst yourselves, I'll take the extra one. This extra one can cause a problem.
Or they get one more, right?
So you could do 34, 34, 32.
I'm not dead.
I'm not dead, and you each are getting a little bit more. The extra coin is actually bad. You could also give the extra coin to either 2 or 4. But the Pirates did find, hey, wait, why are you giving some of our money to There's lots of fun things you can do. I have a counter proposal to make us pirate 1. What?
It's everybody's time.
No, I'm.
We're like, oh, 100.
So do you think I could
Two's
get?
not gonna go along with that. If two's like I could have it. You know what I mean?
So we agree that this is stupid.
Yes.
So is there any way I can try to convince 2 and 4 to vote for me? Is there anything I can do?
Can you give it to somebody, like 3 or 5? Would that make any sense?
I think you would wanna give it to 5, because 5 doesn't really have a chance of getting much at all.
Yeah.
So you might as well throw them something at the beginning, because even if you offered them 2, that would be
Better
more
what
than they
get
would likely
in
get,
savings.
yeah, by the time it, yeah.
So it's all about the money for them.
Yeah, so that's when I was thinking about intelligent, I was thinking that they could all see ahead to all the possibilities that would come after,
Right.
and there was no humanity whatsoever. They were just,
So
We can spend the whole day on this.
no, this is the last thing I was doing. If I did like 51 for 4, I would get 4 to vote.
Yeah.
And then I can give 48 to myself and 1 to 5. And so if I did something like this, if this motion fails, then we go to the 4 pirates and pirate 5 gets nothing. And pirate 4 gets less. So am I able to actually convince pirate 4 to support me with something like this and get more than a third, where I can get almost a half myself? Pirate 5 can still do the bluffing game and say, hey, look, if you don't give me more, I'm going to vote against you. So you are still at risk, but again, you're always at risk of 5 extorting. And if I was pirate 5 here, I would probably argue strenuously enough to move away from this. That if you only give me 1, I realize I'm going to get less, but that's the same logic as before. So I think you can get to the point where pirates 2 and 4 are going to be screwed from this. But I just want to end with, it's really easy to interpret these things in many different ways, to have strategies that look reasonable, but maybe they're not, but maybe they are. It really depends on a lot of the subtleties. Okay. Let's skip the egg drop game for now. Let's go back to the, there's the bridge one. I want to go to the bridge problem. Here we go.
Zombie flashlight one.
The zombie flashlight line. So we're having people walk across the bridge. Their names are 1, 2, 5, and 10. It takes that long for each person to go. You need 2 people at a time maximum. You have to have the flashlight, and you want to cross the bridge in just 17 minutes. And so we started trying to think of good ways to draw things. And this wasn't terrible, but it wasn't keeping track of who has the flashlight. And so we started trying to go through a more elaborate system, where the star represents which side has the flashlight, and over the arrow we're writing maybe who's traveling. So the problem is there's so many things to investigate. Did anybody find a way to solve this or to attack this?
Yeah. Yeah, this one worked out okay.
Okay.
It's not a solution.
Okay, you got a solution?
Yes.
Okay. What was your thought process to get to a solution?
I think realizing that you needed basically 5 and 10 traveling together was most efficient.
Okay, So here's the question. If 5 and 10 do not cross together, how long is the minimum time? So 10 has to go over, right? 10 goes over is plus 10 minutes. 5 goes over equals plus 5 minutes, right? And then 2 has to, and 1 have to go over. So even if 1 and 2 go over together, right? 1, 2 go over, that equals 2 minutes. So that's already 17 minutes, right? But it costs us time to bring the flashlight back. So we need minimum plus 1 minute to get the flashlight back and another plus 1 minute to get the flashlight back. So we know that 5 and 10 have to go over together.
They can't go first.
Good. And then next thing is 5 and 10 do not go over first. That would be 5 and 10 is 10 minutes. 5 goes back. That's 5 minutes. And now it's going to be too much time. So we could look at all the possibilities, but by doing a little bit of analysis like this, we know that it has to start off with 1 and 2 going over. And now it's not so bad. So if we didn't do that, there'd be too many cases. We know we start off with 1, 2, 3, 1, 2, 5, 10, nothing on the other side. And the flashlight is here. And the only legitimate first step is 1 and 2 have to go over. And that's going to cost us 2 minutes. And now we have 5, 10, 1 and 2, and the flashlight is here. Now what do we do?
Send either
back. It actually doesn't matter which one we do. We could send 1 back, or we could send 2 back. If we send 1 back, it's going to be 1, 5, 10, and 2. If we send 2 back, it's going to be 2, 5, 10, and 1. And the flashlight is now over here. And now what do we do? Right. We know we can't send 1 with 5. We've already proved that. And so now we would send, and this is going to now be 4 minutes here total and 3 minutes here total. And so now we send 5 and 10 over. And then that will give us 1 over here and then 2, 5, and 10. And that's going to be now 13 minutes. Now what do we do? Now we would send 2 back. And so then it would be 1, 2, 5, and 10 with the flashlight here. And this would be 15 minutes. And then we would send 1 and 2 over. And now everybody is over and the flashlight is over. And that would be 17 minutes. So
5 doesn't actually matter as long as it's smaller than 10.
So that's a great observation. How much do these numbers matter? 5 could have been 8 minutes, 9 minutes, wouldn't matter. Could have had 2 people as 10. If you make 5 smaller, if you make 5 like 3, does that have people starting to look at it in a different way? So one thing is always, if you want to do a research problem, if I give you 4 numbers, what's the smallest amount of time it would take with those 4 numbers?
What kind of math?
Yeah, it's an interesting question.
Zombie apocalypse.
Zombie apocalypse.
I liked that there was the limit on it, the 17.5.
Right,
Yeah,
right.
it saved you from like thinking you had it.
Well, the other thing is sometimes you can know that there's going to be at least a really bad solution. Yeah.
Have you ever posed it to the students saying, find the least amount of time that you?
For this one, no. For other ones, yes. Anybody here play bridge? So I am the king of multitasking, and when I was on vacation with my family, we actually came up with a bridge problem, which we then published in a journal. And the question is, what is the minimum number of points you need? An ace is 4, king is 3, a queen is 2, a jack is 1, to guarantee that with intelligent play, if the cards happen to be dealt in the best way possible for you, you can make 7 spades. What's the fewest number of points you need? And so we actually originally were just discussing, and I was trying to convince everybody to play bridge. And, I said to my daughter, come on, I'll be your partner and I'll make sure I have 15 points so that I'm at least a good partner. She goes, okay, I want 20. Okay. And so then we were discussing. So if my daughter and I take 35 out of the 40 points and leave just 5 points for my son and my wife, is it possible for them to make 7 spades with just 5 points? And it turns out we actually hit the magic number. 5 points is the minimum you need to be guaranteed that if the cards fall just right, you are guaranteed to make 7 spades if you play intelligently, and opposition plays intelligently. But when I posed that problem, I posed it without saying, how many points do you need? Because when you say certain numbers, it gives people blinders, it gives people ways of looking at things. I will add an interesting problem. So the one we were doing here, you could almost call it maybe part of graph theory. Because I'm drawing a graph and walking on the graph and keeping track of how long it takes as we navigate things. And so maybe something in graph theory, maybe something in elementary number theory, elementary algebra. So here's the graph coloring problem. No connected vertices have the same color. So if I give you, a bunch of vertices and I connect them, what's the fewest colors I need? So if I color this red, I want to figure out how do I color the neighbors? Well, I could make these two here the same color because they don't have anything in common. I could make the one in the bottom red again. I could make this one blue as well because it doesn't interact with any of the other blues, doesn't interact with anything else. I could make this one red and I could make this one blue. And I can't make this one either red or blue. So I would have to make this one green. So the coloring number is at most 3. So I know it's at most 3 because I constructed a coloring that does it with 3. Is it possible to do it with just 2? No, because I have a triangle. I have 3 things that are connected. So the triangle requires 3 different colors. So a better way of starting the problem is I should have started with the triangle, because I know I have to color the triangle with 3 different things. And so I know the coloring number is at least 3, it's at most 3, therefore it's 3. And so here was a problem I proposed years ago. So you have the numbers 2, 3, ... up to
Let me go back to the picture.
Sure.
Doesn't it depend on how you draw the picture? I mean, is that a set picture? That
right, it's for this,
you
right,
can't do that random. That's
well, just for any graph I give you, for any collection of vertices and edges connecting them, what's the coloring number?
so if that green dot was gone.
If that green dot was gone,
It
it would
could
be
be
very
just-
different. Or if I didn't have this edge over here, then I could color that blue.
Okay.
So it absolutely depends on the connections I have.
Is there a way to force 4?
Sure. If I would add another vertex over here, connected to all of them, that would definitely force 4, right? But the question is there another way to do that without putting something that's connected to, without having a set of 4 vertices all connected to each other? Is there a way to still force this? And so, if I put something over here and I connect it to these 3, do I need 4 colors?
But that was the same thing as you just had.
No. No. Before I had it in the middle connected to all 3. Now I'm putting something over here. What I could do now is I could change this from red to green. And if I do that, then I could be okay. And then I could make this red again. And then I'd be okay with just 3 colors. So it's a difficult question to determine how many colors do you need. Okay. So let's say I give you the numbers 1, 2, 3, up to 125. I'll do 126. So we just saw if we have 3 vertices that are all connected, they have to be different colors. So this needs 3. If I give you 4 vertices that are all connected, how many colors do I need?
We have the X in the middle.
Yeah, I have the X in the middle. I would need 4. If I have 5 vertices that are connected, how many would I need? 5. So one way to get a lower bound on the coloring number is, can you find 5 vertices that all are connected to each other? If yes, you need at least 5. Can you find 6 that are all connected? If yes, you need at least 6. So consider the numbers 2, 3, all the way up to 1026. And we connect X and Y if X and Y share a factor exceeding 1. Because if I give you 2 integers, clearly 1 divides both of them. So for example, 21 and 66 both are divisible by 3 and are connected. 21 and 25 are not connected. Okay. So here's the question. Prove the coloring number is at least 10. Can you find 10 numbers that all share a factor? I'm going from 2 to 1026. Does 1026 remind you of any numbers? 10. 1056. It's close to 1056. Not Fibonacci's. So, okay, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So this is just a little bit more than 1024.
So weird, just
Oh, more than a decade ago, the game, I think 2048 was popular for a while. So we have 2, 4, 8, 16, 32, 64, all the way up to 1024. What's true about all those numbers?
Even powers of 2.
Can you give me at least 10 numbers that are all connected?
The ones you just said.
Yeah, the ones we just said, right? 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 10. The coloring number is at least 10. Right? Because all the powers of 2 are connected to each other. They're all divisible by 2. So the coloring number is at least 10.
Sorry,
Yep.
isn't every even number?
Better. All evens gives you at least 513. A lot of students, and I'm the one who proposed the problem, I got confused myself. I looked at powers of 2. And there are 10 powers of 2, and that gives you a coloring number of at least 10. A much better argument is to say, but all the evens are connected. So all the evens have to be colored differently. You can actually prove that it's also 513, that this is enough. Each odd number, you can figure it out. It's a nice exercise. But to me, this is a great problem in how you can put blinders on students and try to get them to look at things in certain ways. I'm giving you numbers, maybe with students, I wouldn't go as high as 10, 26, I'd go maybe a lower number, maybe 65, closer to a power of 2 that they might recognize. And try to get them to be thinking about things like that. And then have them see the powers of 2, and give them a lecture. If you can find a complete graph, a set of vertices that are all connected to each other, that gives you a lower bound for the coloring number. Can you find at least 10? And so I'm trying to get them to look at the powers of 2, but much better to say, just look at the evens. So this is a great example of how we can adjust what people are looking at. I wanted to go from this to the legal 21. All right. Let me just pause this then for a second while I'm trying to find it. Let's take a 5-minute break while I pause and look for this. Okay. So the legal 21 problem. So young Saul, a budding mathematician, has the numbers 1, 5, 6, and 7. He wants to form an ID that says he's 21 years old. He can use any mathematical operation of plus, minus, times, divide as often as he wants, but each operation requires 2 inputs. So these are binary operations. They take 2 inputs, they give you 1 output. This is a nice way to have kids who are just learning algebra, just learning operations, play some games. What numbers can you get? I will allow you to put 1 and 5 together and make 15 if you want. That means you won't have as many binary operations possible, but if you want to do 15 plus 6, that would be 21, but it doesn't use the 7. And so I'm a stickler, all the numbers have to be used. So the question is there a way to get 21 using the numbers 1, 5, 6, and 7? And so I don't particularly care about the answer. I care about the thought process, and just one of the goals is algebra for all. So if you have kids who are playing and just learning how to do plus, minus, times, divide, this is a nice, fun way. You can say, whoever's the first one to get to 21, you get a candy bar or something. How many of you have heard of the 4-4s game? So this is another one that you could play. So the 4-4 game is you have 4 4s. Surprise. And you can do anything you want, and it's which numbers can you get. So for the 4 4s, you could do 1 is 44 over 44, or 4 over 4 to the 44 if you want. There's lots of ways to get 1. 2, I could write as 4 over 4 plus 4 over 4. And you can do, it's an argument as to whether or not you can do a square root. Do you have the square root, or could you do like a 4th root? And so you have to really be clear as to what games are you allowed. Are you allowed to use the exclamation point for factorial? And so you can just ask, which numbers can you represent? And so it's a fun game to see. And at some point, you will probably run out of numbers that you can represent. And then what if I gave you 5 fours, 6 fours? What if I gave you numbers other than 4? What is representable? If I only give you 4 numbers, what is the best you can do in terms of how far you go before you finally can't represent a number? If you only have 4 numbers at your disposal, what's the best to do? Powers of 2, powers of 3 actually would probably work very well for something like that. And if people are interested, we can talk more about that later. It's related to some scaling riddles, equal arm balances. But getting back here, if you're teaching algebra, here's a great way to have kids playing with plus, minus, times, divide, and checking to see if they understand things, if they're doing the calculations correctly. Does anybody have any thoughts as to how we might try to solve this? So what's your first thought? What should you try?
First thought was 6 times 7 is 42.
Good. So one thing is, do I see anything close to 21 that I could try? My first thought was just trying a bunch of experiments, just putting some numbers together, getting a sense of what some things are. 7 times 6 was 42. Is there any way I can get from a 42 to 21? So one thing is, find things close binarily to 21 that we could somehow then get to 21 in a nice way. And you try, and you try, and you try, and almost surely you're not going to see it. There is a solution. My daughter is very insistent that whenever I do games, there has to be a solution. We are allowed to mislead, but we cannot lie.
Can you use a number more than one?
So you cannot use a number more than once. So each number is used once and only once. You can use as many pluses, minuses, times, divides as you want, but remember, each time you use one of these operations, you need 2 inputs. So if I have 4 numbers, I can have at most 3 operations. It could be less. If I do the 15 plus 6, when I concatenate 1 and 5 to make 15, I've lost a binary operation. I could add that as another binary operation, however. I could add the concatenation operation. And so I have plus, minus, times, divide, concatenate. It turns out you can solve the problem without concatenating. You don't have to do something like a 15. There is a way to do this.
Wait, is concatenating the word?
It's like
Putting the 2 numbers?
Yeah, putting 1 and 5 together to make 15. Yeah. I think
I've
that's,
never
I think
heard
So
that
we
word
can't do
before.
that.
you can. You don't need to. You don't need to. You don't need to. There's a solution without doing that.
How do you spell it? Is that concatenate?
I'm not sure that's the right word. Is that the right word?
Probably.
Concatenate. I'm surprised it says nobody searched this on the Google phone yet, or Android, iPhone. I think concatenate is right.
I'm not doubting you.
I am. I'm also doubting my spelling. I was a huge fan of Shakespeare because he established you can spell the same word multiple ways in the same line.
Have 10 eights.
Ian.
So Ian.
Ian?
Yeah, that's an E-O.
Okay.
It might be a little bit hard to read. Let me make it a little bit easier to read. So the way I would solve this is actually related to my poor spelling, but I'll say my great verbal skills. In the 21st century, you should be more than just one thing. You should have multiple skills. And one of the other subjects we teach students is English. How many of you remember your elementary school, middle school English? Diagramming sentences? Probably the most mathematical thing you did in English. We can play a similar game here. We have binary operations, they take two inputs and they give one output. So we could look at 6 times 7 divided by 5 minus 1 as we do a binary operation of multiplication on the 6 and 7, a binary operation of multiplication on the 5 and 1, and then a division of that, another binary operation. So we can view this as 3 binary operations. Combine 5 and 1 with multiplication, combine 6 and 7 with multiplication, and then combine those results with division. This is a possible sentence structure. And so I can look at it as, here is one possible sentence structure. Do a binary operation on inputs W and X, a binary operation on inputs Y and Z, and then a binary operation on all of them. And what I can then do is I can loop over all the ways to put the numbers 1, 5, 6, and 7 as W, X, Y, Z. So how many choices do I have for W? 4. How many choices do I have for X after choosing W? 3. So I have 24 choices of order for W, X, Y, Z.
Is the B2 always multiplication?
No.
Okay.
So how many choices do I have for the first binary operation?
4.
And the second?
4.
And the third?
4.
So I have 4 cubed, and I apologize if that sounds bad, choices for the binary operations. So I have 24 times 16 possibilities for that sentence. Yeah, exactly. And then,
What? Times 6 cubes?
sorry, times 64, times 64, times 64,
Okay.
times 64, sorry.
Thanks.
Yep. So I have 24 times 64. Roughly call it, 20 times 100. So call it roughly 2,000, just ballpark. Yeah. So I'm saying that's a lot to do by hand.
Yeah.
And now this is one possible sentence structure. Remember when we analyzed tic-tac-toe, we talked about there's 9 opening moves and there's 8 responses, or we could be intelligent and say rotate, there's up to equivalence, there's 3 opening moves, corner, middle, center. That's what we're doing here. Rather than analyzing all the cases in an ad hoc fashion, we're just randomly trying things and hoping we get lucky, we're trying to be methodical. This is still not enough for a human to have fun, right? Because there's more sentence structures than this. But, if my life depended on it, I can try 2,000 things.
What about James's life?
I could try 2,000 things for James's life as well. I'm not as motivated. I'm more motivated. But then, of course, the question is, how many sentence structures are there? If there's 1,000 sentence structures, then that's really bad. It turns out there's only 5 sentence structures. So, well, on the order of 10,000, I can do this. Worst case, does everybody agree I can do at least 10 a day? I'm sorry?
For 3 years.
For 3 years. So 10 a day is not hard. I mean, how many of you do a daily challenge? Some daily challenge. Yeah. So this isn't that bad. You put this on Facebook, and you do it like a distributed computing. Everybody's going to get this set of 10 to check. And we can do this really quickly. A lot of things do this. The Search for Extraterrestrial Intelligence did a lot of stuff like this. A lot of I don't know if the Human Genome Project did shared computing for stuff like this, but there's been a lot of things that have been farmed out and a lot of people have contributed. Prime numbers, number theory has had a lot of stuff like that. So now you can talk to your students about how many different sentence structures are there. And so it turns out, here's the answer. There's only 5 sentence structures. I can combine WX, I can combine Y and Z, and then I can combine their results. I can combine W and X, and then combine that with Y, and then combine that with Z. I can combine W and X, and then combine that with Y on the left, because the order in which I combine them matters. If it's addition, it doesn't matter. If it's subtraction, it matters. If it's division, it matters. So depending on which binary operation I do, it makes a difference which order I do things. If I wanted to speed things up, I could actually have more sentence structures and then have the binary operations split between multiplication and addition, which are commutative, and subtraction and division, which are not.
Well, because like the first one, if it's all addition like that, then it actually
Right,
doesn't matter.
it doesn't matter. But if I have a subtraction, then the order matters. So if it's all addition, WX and Y and Z, if I flip WX and Y and Z, it doesn't make a difference. There's so few cases to study, you will spend more time coding that than just checking all the cases. So when I wrote the computer code to do this, I did not bother to put in anything like that because I knew it would take me more time to write that. I tell the computer, here's the 5 sentences, for each one of them check. Don't do anything to save yourself time. What's one of the things you have to be careful about when you're doing something like this? What could happen as you're doing these operations that you're not allowed to do? As a mathematician, there's something you're not allowed to do. Divide by 0. I was about to pull it up, but you got it too faster than I could. I believe I have the oldest membership card for the American Math Society that is still in active circulation. This is from before 2000. And so everything is electronic, of course. There's no need to have a paper copy anymore. I am a card-carrying member of the American Math Society. I am not allowed to divide by 0. You are not allowed to divide by 0. Should you put in some code to say, thou shalt not divide by 0? I have 1, 5, 6, 7. If I do 1 plus 6 minus 7, that's 0. So I do have to remember that. So what I do is I just put a line in the code that says, if you are dividing and the number is 0, then just say not a solution. But what I like about this problem is, if you're teaching algebra, this is a way to try to get kids to practice their basic skills and ask them to think, what are the possible sentence structures? Break them up into groups and see who can find the most structures and say, if we have x plus y divided by w minus z, this is really the same structurally as x times y plus w divided by z. That structurally, those are really the same. And this idea of trying to teach them, how can you go through stuff like this? If you code the sentences, can you do this with a Google Sheet where you put in the numbers? If you specify what the algebraic operations are, yes, you can do this on a Google Sheet. Can you do a Google Sheet where you're now choosing which values these are? That's a little bit harder. There's 64 possibilities, so break it up into the different sentence structures, not just like this, but with what the actual operations are. It's a good way to start talking to the kids about how do you do programming. And so the final solution is 6 divided by 1 minus 5/7. And the oomph is right. This is why people almost always miss this, because there are 2 divisions that are needed. But there was a comment in the very beginning that let's start by looking at 7 times 6 is 42. And we really do have the 7 times 6. So the intuition of trying to look at 7 times 6 is 42 was a great way to start. What was challenging is how do we get to, we don't get to 7 times 6 by multiplying them. Why would we do that? We get to it by a double division. And a double division, okay, that is the same as pulling it up into the numerator. So this is one of my more enjoyable problems because it provides a lot of opportunities to practice algebra, to tie in what you're doing to another class. It's always nice to say, hey, where the teaching and other things matters, here's where this sentence structure idea matters. Most of us don't really care about this is the verb, this is the adjective, and diagramming something like that. But this idea of, can I break something up into a certain structure and then attack them all with similar methods? That's extremely important. Okay, any questions about this one?
I've done something like that, but it's not where a fraction within a fraction.
Right.
Yeah.
No, there's a whole slew of problems like this. And this one is particularly nasty because it's two divisions. And again, it's what are our blind spots? What are we just instinctively shying away from?
Yeah,
And so-
I'm just trying to think of like, is there a way to see the two? So that you aren't like computing brute forcing, you know what I
Right.
mean?
I mean, it's really 7 minus 5 over 7.
Yeah,
And we get that extra 7 for free because of the subtraction of 1 minus the fraction.
yeah, because one's not really a one.
Because one's not really 1.
Right.
1 is really 7 sevenths.
Yeah.
And one of my professors at Yale, Peter Jones, once remarked, there are only 2 things you can do in mathematics. You can add 0 and you can multiply by 1. And he said, the log of 1 is 0. There's really only one thing you can do in mathematics. But it's really good advice. When we prove a lot of things, you often multiply by 1 in a clever way to then help tell the story. So I will use this as an opportunity to do one of my favorite asides. How many of you have seen Pascal's triangle? So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Has everybody seen this at some point? So the rule is each number is the sum of the number above to the left and above to the right. And these coefficients, this comes from expanding x plus y to the 4th. These numbers have a lot of important properties. So we say n choose k is the kth entry of the nth row. It turns out this equals n factorial over k factorial n minus k factorial. And everybody has seen the factorial. It's multiply all the numbers down to 1. So 4 factorial is 4 times 3 times 2 times 1. We talked about that, I know, briefly on the first class when we just talked about how big 9 factorial was. So there's a combinatorial interpretation. This is the number of ways of choosing k objects from n when order doesn't matter. So choose k from n, order does not matter. So there's a lot of beautiful stuff you can do with Pascal's triangles. There's a lot of tremendous properties. The big one here is n choose k. Did we talk all about this last time? I don't think so. Okay. This might be better to do in the afternoon when people are a little bit more tired. We'll do it now.
Yeah.
Well, no, because it's story time. So here's the first theorem. N choose k is n choose n minus k. And the proof is algebra. You look at n factorial over k factorial n minus k factorial versus n factorial over n minus k factorial n minus k factorial. But what's n minus k? I take n and I subtract n minus k. It's just k. So this is equal to n factorial over n minus k factorial k factorial. But that's the same thing. I just wrote them in a different way. So this is proof by algebra. I just showed that the two sides are equal. It gives me no understanding why it's true, but it's a proof. Proof by story. Dr. Seuss. So how many people still remember the Dr. Seuss? I once got into a cat in the hat off with one of my colleagues at Brown as to who could go further. And unfortunately, he had a huge advantage because he not only had kids, he had grandkids. And so I ended up, I could get through like a quarter of the book without a trouble. He beat me. How many of you have read the Sneetches? The Sneetches is the proof. Oh, excellent. And since you are so familiar with the Sneetches, which Sneetches are the best on the beaches? The ones with stars or the ones without stars on their bellies? Who are the best sneechers?
And what part of the story?
Manipulate.
By the end, by the time we've learned everything we need to.
They're all the same.
They're all the same. They're all the same. It doesn't matter if you have a star or if you don't have a star on your belly. And so it's a great book. So the sneechers initially are led to believe if you have a star on your belly, you're a special sneech. So all the sneechers that don't have stars on their bellies get stars on their bellies, and it costs them money. And the person who sells them the stars sells star removal to the ones who had stars initially, because now they're really good. And so they keep going back and forth until they have no money left, but they do learn a very valuable lesson that it doesn't matter if you have a star or not. It just matters you root for the Red Sox. So all that matters is that you're a sneech. If I'm choosing K people out of N to get something, and only those K people get it, that's the same as choosing N minus K people to exclude. So these are really the same by telling the story. So I could do the algebra, and when I'm done with the algebra, I don't really have a sense of why this is true. Or I could tell a story that if I'm choosing exactly K to have something, that's choosing exactly N minus K not to have something. And so this is proof by story. It's one of the best techniques we have, but it's sometimes very hard to do. And the reason I am doing this digression right now, I almost said diversion, I hope it's a diversion as well, definitely a digression, is that it is related to something we were talking about a moment ago, which we will see very shortly. So here's our second theorem. N plus 1 choose K plus 1 equals N choose K plus N choose K plus 1. And one proof is algebra. I can just do the algebra by brute force, expand everything, clear denominators, simplify the algebra. And when the dust settles, I will have a proof. It's unenlightening, I don't know why it's true, but I have the result and I can now use the result. Better proof is by story. So I need a good sports team. Red Sox, excellent. So we have N Red Sox fans. And I need a horrible team. Oh, the White Sox, okay.
The Mets.
The only issue with the White Sox is if I wanted to write White Sox in white, it would be hard to see on the whiteboard. So we'll go with the Yankees.
The only reason we're going.
It's the only reason we're going with the Yankees. So I want to choose K plus 1 people from N plus 1. Okay. I have N plus 1 people total, right? And Red Sox fans, 1 Yankee fan, there's N plus 1 people. I want to choose K plus 1. By definition, it's N plus 1 choose K plus 1. That's how we define the binomial coefficient. It's how many ways are there to choose a fixed number of people from a set of people when order doesn't matter. There are two possibilities. I either have the Yankee or I don't. So imagine we have the Yankee. So have the Yankee and then no Yankee. How many ways are there to choose 1 Yankee fan from a set of 1 Yankee fan? 1. But I'm going to write 1 as 1 choose 1. And now I need to choose how many fans from the Red Sox. I've got 1 Yankee fan. I want K plus 1 total. How many Red Sox fans do I have to choose? K. So it's times N choose K. Now imagine I don't have any Yankee fans. How many ways are there to choose no Yankee fans from 1 Yankee fan? That's 1 choose 0. And now I need to choose how many Red Sox fans. K plus 1. I want to have K plus 1 people. I haven't chosen any Yankee fans, so I have to choose all K plus 1 from the Red Sox. So N choose k plus 1. So this is a proof of this relationship. So we define 0 factorial to equal 1. It's a very convenient thing, how many ways are there to order nothing? There's one way to do nothing. Right? What's the greatest show in TV history that does nothing? Seinfeld, right? There's only one Seinfeld. And why are we watching this? Because it's on the air. Not yet. So the 0 factorial, it's very convenient to define it to be 1. So 1 choose 0 equals 1 choose 1 equals 1. When I'm looking at this relationship, notice the top and the bottom are almost the same. They all have the n choose k, they have the n choose k plus 1. But I don't have anything in front of these. What I really have missing here is I have 1. And this one is 1 choose 1, and the other one is 1 choose 0. We really just multiplied by 1 in a clever way. And sometimes the way a formula is given to you, it's not the easiest way to understand. When you look at it this way, the top is n plus 1 on the left, but the top's n on the right. The bottom is k plus 1 in 2 places and k in another. If I do it like this, notice the tops always add up to n plus 1. And notice the bottoms always add up to k plus 1. This is a much more natural way to look at what's going on in my mind and understand what's happening. I've got to have n plus 1 total. I've got to have k plus 1 total. This is telling me how to split things. And so if people like stuff like this, there's a lot more you can do with Pascal's triangle. There's a great connection to fractals with stuff like this. And if people are interested, I'll arrange for video after lunch. But this is just a great way, going back to the legal 21. There was that wonderful comment that 1 is not really 1. It is, but it's really functioning as 7 sevenths. And we get it for free like that because of the subtraction with the division. And so we're writing 1 in a better way. And so much of math is, can you find a good way to multiply by 1? Can you find a good way to rework things so that you can actually do the algebra? These proofs are hard. The algebra proofs are really easy. They may not be pleasant, but you roll up your sleeves and just multiply everything out, clear denominators, keep working, keep working, keep working. You will get it. Finding the right way to look at a problem so that you can see the simplifications, that's much harder. But when you do this, you can improve a lot more. So again, if people are interested and want to do modules like this, there's a whole slew of problems that I can give that can then be interpreted in terms of stuff like this. Okay, so trying to be cognizant of the time and when is the best to do various things. If there are no questions on this, I think this is a good time to do the egg drop problem.
I guess I have like a non-recording philosophical question.
Okay, unfortunately, I can't do non-recording philosophical questions. That's not recording. So the egg problem. So the egg drop problem is one of my favorites. It is all it is cracked up to be. You have to have fun. So we talked about the statement before. These are special golden eggs. Has anybody seen this problem?
Our Minuteman Tech program does it and has them actually do it.
Okay.
They have an egg and they have to go through testing it and everything.
Okay. And so with these, there's a building with n floors, because what are the number of floors we have? And these eggs are such that if you drop them below a certain threshold, there's no damage to the egg. Even if you drop it 1,000,000 times, no damage. But as soon as you drop it from a certain floor or higher, the egg shatters and breaks. And I want to figure out, where is that floor? And I don't care how many eggs I have left at the end of the day. I just want to know what floor it is in the fewest number of drops. And so, again, with a question like this, you can always ask, what exactly am I trying to minimize? Is the bad floor equally likely to be every floor? Is it more likely to be a higher floor than a lower floor? If I know some information like that, am I maybe trying to minimize the expected number of drops? Or maybe I'm trying to minimize the worst case scenario. If the floor is chosen as nefariously as possible. If anything that could go wrong for my method goes wrong, what's the worst case for me? How many drops would it take? And for a lot of things, we do worst case scenario. And so that's not a bad way to do the estimates. And so we talked about how do you interpret this. So minimize the worst case, minimize the average case. Anybody have any thoughts as to how we should start this problem? And it's related to something we've already seen today.
Well, I was like, just worst case scenario is you start at 1 and go all the way up until it breaks.
The n+1.
Or you start at n and it goes all the way down to 1.
Okay, okay. You're looking at the wrong problem.
I was thinking like go start right in the middle and then cut it in half.
You're still looking at the wrong problem.
We're talking about trying to minimize the number of.
So I'm giving you have 2 eggs, and I want you to minimize the number of problems to look at. Is this the problem you should be looking at?
You run out of eggs.
I don't care if you run out of eggs.
Worst case? Yeah.
Well, if you break both, then you don't have your answer.
So you have to get the answer at the latest by the second egg breaking. But just because I'm giving you this problem, I have a building with 2 eggs, doesn't mean that that's the problem you should look at first.
Stores is the building.
N. What problem should you look at first? I'm trying to give you a hint. So one is you could change the number of floors. That's one possibility. Is instead of doing a building with n floors, I could do a building with n-1 floors. And I could keep going. What if I have n-2 floors, n-2?
Yeah. What does I have to do with it? Like, I don't know, you're closing your one eye.
I know. I'm a pirate. I don't have an eye patch on me. I'll say fortunately, I'm glad I don't happen to have an eye patch on me because of me. What did we learn in the pirate problem?
Start at the top.
Nope.
You start with 1.
You start with 1 pirate.
So you start with 1 egg.
Start with 1 egg. Right? Don't try to analyze the 2-egg problem with n floors. Right? This is a general principle. It doesn't matter what they give you. Start with an easier problem first. Solve that. Because what happens as soon as an egg breaks? You're down to the 1-egg problem. So we should do the 1-egg problem first. Understand the 1-egg problem. And then once we understand the 1-egg problem, then we can do the 2-egg problem. And guess what comes after the 2-egg problem?
3 egg.
Exactly. All right. So what's an easier problem? The 1-egg problem. So what is the only possible strategy that's guaranteed to work in the 1-egg problem? Start at the bottom and go up. So you have to do 1, 2, 3, ... Worst case, I would say n. Worst case, you try every floor, or maybe n-1. If I know that it has to break, if it hasn't broken. So if I tell you that it has to break, we don't know.
But the most you could drop it is n amount of times because that's how many floors.
Correct.
But if you've done all the floors but 1, we wouldn't drop it again.
Correct. So if it doesn't break for the first n-1 floors, if it has to break, then I know it has to break on n.
Wait, is n the number of floors?
N is the number of floors.
Yeah. And you don't know what floor.
Correct.
So we don't have a different ladder for the floor that it breaks at.
No.
Okay. I think that's fine.
Okay, so it breaks on some floor, we don't know what floor. And so it's either n or n-1. If I know the egg has to break, then if it has to be broken by floor 99 and I have 100 floors, it breaks on floor 100. Maybe the egg doesn't have to break. Maybe every floor is safe, in which case I would have to do all of it. I don't really care about the +1 or the -1. I just care it's on the order of n drops. So if I did anything else, if I dropped it on floor 2 and it broke, I have no more eggs, and I don't know would it have broken on floor 1. I am stuck. I have to do this. I have no choice. Okay. So worst case, it's on the order of n drops. Okay, now with 2 eggs, once an egg cracks, we are reduced to the 1 egg problem. So what are possible strategies? Good. So one possibility is every other floor. So 2, 4, 6, dot, 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 till break. Then do one more drop. So this is a great strategy because as soon as it breaks, we're now within 1. And we can find that very quickly. Like, worst case scenario, how many drops? And it's okay if you're off by 1, just approximately how many drops, worst case.
And over
Two plus one.
And over 2 plus 1. Something like that. I might be off by a little bit because maybe I don't have to do the n over 2, but maybe if I don't know that it breaks, I do have to dry up the last one. So it's basically n over 2 plus 1. That's a really good strategy. Can somebody give me another strategy? Somebody had mentioned this earlier.
Starting in the middle.
So you could do start in the middle. So you could do the middle. If it doesn't break, what does that mean?
So it's higher.
It's higher. And where would you drop next? Middle down.
Middle again.
So you can do middle again, middle. So each time you winnow by a factor of 2. What if it breaks in the first try? You have to start from 1. So the worst case here is 1, and then we have about n-halves to do. I might be off by 1 over here, but they're basically about the same. Notice they are very opposite. So if doesn't break, you eliminate a lot. But when you break, a lot to check. Your strategies are basically opposites of each other. One of them is, once it breaks, I've really localized it. But it could be a long time before it breaks. The other one is, once the longer it goes before it breaks, the more I eliminate, and I can eliminate a lot. But once it breaks, I could get really stuck. Any thoughts about what we could do as a third strategy? So we did every 2, we did the middle. So you could do every third, right? And after we analyze every third, what could we do? Every fifth, every fourth, right? So why don't we just do every x? Because it's going to be the same analysis. So if I was doing this with students, I would do, let's do every third, let's do every fourth. Do we start to notice a pattern? And then let's try to do it in the general case. So let's do every x. So worst case scenario, we do x, 2x, 3x, dot, 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 dot. How many drops would it be before it breaks? Worst case. How many multiples of x do I need before I get to n? So let's do numbers. If n equals 100 and x equals 5, the number of drops is what? Is n over x, which would be 20. So the worst case scenario here is going to be n over x, right? That's the number of drops. If I have n over x steps of size x, that's going to take me all the way up to n. What's the largest I can multiply by x by to get to n? N over x. N over x times x is n. So I have n over x drops. And now from this point onward, how many more do I have to do? So once it breaks,
n minus 1.
not n minus 1, x minus 1. Now, really, the x and the 1 are really grouped together. And so I'll make them red, because the x minus 1 is coming together. But I'm choosing mentally in my mind to group the x with the n over x. And the reason is, as I change x, the first part, n over x plus x, changes. the -1 doesn't change. That's a fixed cost. So in terms of my mind, in terms of how I analyze this, I want to find what value of x makes this as small as possible. I don't really care about the -1. If I want to maximize or minimize something, if there's a constant that I'm subtracting off, well, that's always going to be there. So I might as well just try to make n over x plus x as small as possible. When x equals 2, good, it basically does reduce to what we had before. Maybe we're off by a little bit with the -1 and +1. I'm not worried about that. I hope nobody here is worried about that. So is everybody comfortable that this is a strategy? We can compare how does this do to other things. So we have every 2 was basically n halves plus 1. The middle was basically 1 plus like n halves minus 1. Every x is n over x plus x minus 1. So if we put in some values of x, do you want to take n equals 100 just for niceness?
Yes.
We could do 120, which is divisible by a bunch more things.
I like 100.
And we'll do 100. So we'll take n equals 100. So when x equals 2, we get 50 plus 2 minus 1 is 51. When x equals 3, it's basically 33 plus 3 minus 1. So that'd be roughly 35. Right? So if I take x equals 4, we would get 25 plus 4 minus 1, 28. Also, if I just keep taking large x, it's going to keep getting small and small. Do you agree with that? So eventually it's going to tip. And so I will just try to move.
Still 2 eggs, right?
This is 2 eggs. And then this is the advantage of using the iPad and not the screen. So let's go at the other end. Whoops. What's a large value of x to take? 50. So if I take x equals 50, then I would get n over x, which is 2 plus 50 minus 1 is 51. Whoops. It got really large. What if I take x equals 25? Then that would be 4 plus 25 minus 1. Oh, no, it's not surprising that there's some relationship between some of these x's. Anybody have any thoughts as to what the best value of x might be? So if I do x equals 5, I would get 20 plus 5 minus 1 is 24. So it's still getting smaller. And we know eventually it's going to start getting larger. So okay to be wrong. Anybody have any number they want to guess might be the best? 10. The 4 and the 25 are linked. The 2 and the 50 are linked. Patterns. 2 and 50 give us 100. 4 and 25 give us 100. So to get more data for this, what number should I check over here? 20. So if I do 20, I would have 100 over 20, which is 5 plus 20 minus 1 is 24. So maybe try 10, 10. And so if I do x equals 10, I would get 10 plus 10 minus 1 is 19. It turns out that's the best.
Would it work the same if n wasn't a perfect square?
It would. It's not the best solution. There's a slightly better solution using some number theory and triangle numbers, but roughly the square root is where you want to be. Did everybody learn calculus in the past week? Okay, so I should continue assuming people do not know calculus. But of course, your students know calculus, right?
The students are 10.
This is being recorded. My daughter sometimes gives me trouble because I didn't learn calculus until I was in high school. There's advantages and disadvantages to having a father who's a math professor. So we've talked about 2 eggs. As soon as 1 egg is broken, we reduce to the 1 egg problem. You named the strategies that I was hoping you would name. These slides were prepared in advance. Drop every second floor, drop it n over 2. These are the 2 opposite extremes. I do not expect you will be dropping eggs or other things from buildings, right? We were told very recently, I think it was Lisa, that has a colleague who's really good at the who gives a question. And we will see in the next few minutes why we actually care about this problem. There's a really good math concept looking behind here. So we analyzed basically the 2 strategies take on the order of n over 2 drops, dropping every second or dropping in the middle. It's not that good. It's still on the order of n. We talked about dropping every x floors. It comes down to reducing the function n over x plus x. I don't have to worry about the minus 1 because that's a fixed cost. And so can we find which x makes this as small as possible? When you look at this, somebody give me an argument for making x a certain type of number. Why would you want x to be big?
Because it's a denominator.
Because it's a denominator. So the bigger x is, the smaller the first fraction is. But the bigger the second is. So that means you want to make x small. So you now have a fight. No, sorry, fight is wrong. You now have a discussion between the first pirate, n over x, and the second pirate, x. And they have competing interests. I want x large, I want x small. We need to compromise. What's a good compromise? We could do the, I want everything, screw you first fraction, I want to be as small as possible. But then that's not going to be good for the team, because now the team is a combined score. And so it doesn't matter if your score is low, it's the combined score for the team. Great, you're shining in your part. So my wife and I had a difference of opinion when my son was very young and he was put in the outfield and not at second base on one of these summer all-star teams. And my wife said, our son is the better second baseman. It's like, yes, but he's also the better outfielder. And it's better for the team to have the better outfielder with all the balls that get into the outfield than to have a slightly better second baseman. And for the team, this is a better allocation of the resources. So we have 2 competing arguments here. I want x large, I want x small. You can't get both. They have to compromise. Any thoughts on what would be a reasonable proposal? So,
do we know anything about x versus n?
Well, you have to tell me x is a function of n.
Right.
Okay, so why would we take x to be square root of n? What does that do? You're right.
Middle ground.
Middle ground. Why is that the middle ground? What does that do to the 2 fractions if x is the square root of n?
2 root n.
Oh, just makes
That's what it makes it.
plus. Well, the first one would just be.
The first one would be square root of n, and the second one would be square root of n.
Right.
So if I take x to be the square root of n, I actually equalize the 2. So
So both parts are the same.
So both parts are the same. Exactly. And so
neither side wins.
So neither side wins. So yeah.
Yeah.
So I don't know why, but sometimes it doesn't put the exponents in the right spot. So I will draw out the 2 like that. Okay. And we're here. So So you're gonna get a problem. I have n over x equals x. I want to equalize the two expressions. So that's the same as n equals x squared, or x is the square root of n. This is not a proof that this is the best. Maybe it would be better to have an improvement in the first at the cost of the second not being as good. I have not proven this is the best. I've just shown that here's a really good suggestion. If I equalize the two, then I'm going to get square root of n for the drop every square root of n floors. And what's nice now is if I plug that in, I get n over square root of n plus square root of n minus 1, which is about 2 square roots of n. Notice that the initial every 2 or halfway, that was n halves. This is much, much better for large n. If n is 10 to the 10, square root of n is only 10 to the 5. N halves is still basically 10 to the 10. This is a tremendous savings for large n. Square root of n is much, much smaller. This is not a proof that this is the best we can do. And it's really important to emphasize exactly what we have not done. We haven't shown that the best strategy is to drop every x. And even assuming that dropping every x is best, we haven't shown that this is the best value of x to take. We've just shown if we take x to equalize the two competing influences, then we can do it in square root of n. We'll now show that this is actually the best. So here's a plot. I plotted it when n equals 100. And when you look at this, it does seem quite convincing that 10 is the best you can do. But maybe the plot looks different if instead of 100, I had 1,000, or if I had 314, or I had 1998, right? Hopefully not. So this may be more than you want to do with your students. If so, not a problem at all. It seems like it's coming up. Okay. So a little bit of advanced stuff, which is not bad to do every now and then. What I can do is I can rescale things. From the calculation we just did, we believe that the square root of n is probably the critical threshold. So rather than writing my thing as x, let's write x as t times the square root of n. So t is going to measure how far am I from square root of n. So I'm just changing variables. And so wherever I had an x, I put in t square roots of n. And now I get n divided by t square roots of n plus t square roots of n minus 1. I get square root of n over t plus t square root of n. I can pull out the square root of n. And my function is now just 1 over t plus t. There's no longer an n dependence. I now have a function that's independent of how many floors there are. And I just have to analyze this function and see where this is smallest. And it's not that bad to show that it's smallest at 1. We talked about do dogs know calculus last time. We talked about what do you mean. We talked about the arithmetic mean and the geometric mean. This is related to something like that. The geometric mean of 1 over t and t, I would multiply them and take the square root. That's 1. The arithmetic mean has to be at least 1. The arithmetic mean we showed is always greater than or equal to the geometric mean. If I take t equals 1, I get the geometric mean. Basically. I'm supposed to have my divide by 2. You can put that in later. T equals 1, you can show is the best you can do using the arithmetic mean, geometric mean. The key idea here is by rescaling x, we remove the number of floors. And say, I don't need to know the exact solution. I just need to know the solution is roughly of size square root of n. So if I choose my units like that, I can now make my calculation independent of the number of floors, and this is the best I can do. And I'm doing much, much better. And so if you know calculus, how many of you remember calculus? Okay, so if you remember calculus, you can start doing games by taking critical points, checking the endpoints, and doing all the calculus, and you actually can see that this is going to be the minimum. But we were able to prove that if you do every xth floor, the best you can do is the square root. We were able to do that without calculus. So it is amazing how far you can push the algebra. So why do I give a? So imagine you have two algorithms. one algorithm always takes 1,000 seconds. How long will it take to run? Yeah, this is just who's awake, right? It's 1,000 seconds, right? The other one takes 1 second, except 1 in a million inputs takes 1 billion seconds. Both on average take approximately 1,000 seconds. Which algorithm do you use? One input.
The second one.
It could take you 1 billion seconds.
Oh, it's not like consistent, like the
So
first,
just
and then it's not the millionth one that takes a day.
right, you just know that there are certain inputs that take it a long time. Most of the time it can quickly determine things, but every now and then it has something that causes it trouble. And for those,
One in a million ways.
so it's how risk averse are you? And you, again, this goes back to a real theme of the seminar. How risk averse are you? Right? If you're willing to take the risk, algorithm 2 looks much, much better. But you do expose yourself to a 1 in a million chance of something being really bad. 1 in a million is not that bad.
Oh, 1 billion seconds.
Yeah.
So 3,600 seconds is an hour, right? So call it 10,000 over 3 seconds is 1 hour. How many hours are there in a day? So call that 100 over 2, right? So that's hours per day. How many days in a year? Call it 1,000 over 3 days per year. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 9th over 9 over 18. So that's about 10 to the 7. Here, about 5 times 10 to the 7. Because 18 is really like 5 times 20. If I put the 18 is like 100 divided by 5. 20 is like 100 divided by 5. So if I want to just roughly estimate this, this would be roughly 10 to the 7, 5 times 10 to the 7 seconds in a year. And we have 10 to the 9 seconds. So this would be over a year. This is just getting a quick rough ballpark estimate of how is it. And so rather than having the actual numbers, I'm just putting in 3s, 2s, and whatnot. So this is on the order of a couple of years.
Yes, it depends how long you.
How many inputs are we gonna do, like, that, that's like,
There's only one input.
If you need the answer.
what if,
in
like,
five-
how many times we're gonna check different input, and then you're only putting one in at a time. Right,
But if you need the answer in 500 seconds, then you might as well do the second one because you can't get it in the first one anyway.
Good. So one possibility is sometimes if you take too long, the deal is no longer on the table. And so I can only wait 5,000 seconds. If you can't get me an answer in 5,000 seconds, I don't care. And so in that situation, I would always choose probably algorithm 1. Or if I need something in at most 10 seconds, then I would have to gamble and choose algorithm 2. But like most things in life, it doesn't have to be an either or. So what if I run algorithm 1 and it takes more than, this should be run algorithm 2. So what if I run the second algorithm? And if it takes more than 2 seconds, I know it's in one of the really bad cases. And then I switch to algorithm 1. So I can switch between the 2 different strategies. I start with algorithm 2 because most of the time it's going to just be 1 second. It's always, what do you have available? In high school, before Christmas break one year, in physics, we decided we were going to play, or the teacher decided we were going to play like a Trivial Pursuit game. And I was one of the 2 captains. And I had a really good idea. And I decided it was such a good idea, nobody else would think of it. And I'll just wait a little bit. So we start picking our teams, and I wait a bit. And then towards the end, I pick the teacher. And the teacher goes, Wait, Mr. Thurwood, are you playing? I guess I am. And so I didn't want to waste one of my earlier picks on him because I figured no one else would think to pick him. So it's what can you get away with? What are the rules? And so I never said you have to use just one algorithm. I said, what algorithm would you use? We can check the video.
That part was being.
That part was being important. How many of you have read either Flowers for Algernon or seen the movie Charlie or the play? It's one of my favorites of all time. And there's a scene when he's very upset that he has been misled before his intelligence was boosted. So no, check the tape. And he was misinterpreting what was being said. And his memory was playing small tricks on him. And so I may have misspoken if somebody wants to check the language to see if I actually said you have to use. I thought I said, which algorithm would you use? Which is implying, absolutely implying, but it's not forcing, it's not mandating. The best strategy here is to switch between the two. In some sense, this is what we're doing with the egg drop problem. And to me, this is one of the reasons why I love teaching this to kids, is that you don't have to lock yourself into one thing. You can be dynamic depending on how things are going. You can adjust. I have two different strategies, the drop every second or drop halfway. They both have pluses and minuses. What's a good compromise between them? They're pulling me in different ways. How can I find the best? Just for some technical things, please feel free to tune out and already think about where you're having lunch. It's a little bit better not to drop every x. So drop x on the first time, x minus 1 on the second, x minus 2 on the third, because every time you drop without it breaking, you've increased the number of drops by 1. So it's a little bit better to drop a little bit further on the first one, because if it breaks in the very beginning, that's great. You haven't had a lot of bad drops. So you drop a little bit further on the first and a little bit smaller. That's the best you can do. It's still going to be roughly square root of n, but it's a little bit better. This leads to triangular numbers. So let's just move this up. So for instance, if n equals 105, we would drop it on floor 14, then 13, then 12. And 105 is carefully chosen to be a nice number. So now you could ask, what would you do if you have 3 eggs or k eggs? I'm not going to go through the details now. If anybody's interested, I've actually written this up with kids who are in elementary school. So the kids in elementary school are the authors on a paper on this and trying to figure out how would you generalize this. So for 3 eggs, as soon as 1 egg breaks, it's the 2-egg problem. So you can go through and you can start analyzing. So I drop it every x. So drop every x breaks. It's the 2-egg problem with x minus 1 floors, right? Does everybody agree? So the number of steps, worst case scenario, it's going to be n over x plus 2 egg with x minus 1 floors. Yeah. Is everybody comfortable with that? Well, to just make my life easier, this is basically n over x plus 2 eggs with x floors. I don't want to deal with the minus 1. And so this is going to be n over x, and then we just showed it was 2 times the square root of x, and then there might have been a plus 1. So there was a minus 1 at the very end. It's 2 squared. But the minus 1 doesn't matter. And so I need to minimize n over x plus 2x to the 1/2. Okay, it's been 5 minutes. Have you all learned calculus? Slackers. So how could we figure out what size should we make x? Well, the limit point would be as we add more and more eggs. Yeah. What do you think the answer becomes as you add more and more eggs? So what should we do here? I've got n over x and I have x. The first makes x large, the second makes x small. What should we do to get a good choice of x?
Somewhere average.
Average how? What did we do before?
Before we made it, so like both parts were kind of weighted equally.
Yeah.
Them equal to each other.
So one possibility is set equal. Yeah. So we could say n over x equals x to the 1/2, and to make the two terms equal. And that's going to imply that n is x times x to the 1/2. So n is x to the 3/2. So x is n to the 2/3. Yes?
I mean, it's true, I just don't like it.
I'm just making sure I didn't do the algebra wrong and have egg on my face. So the cost is n over x plus 2 square roots of x. So it's going to be n over n to the 2/3 plus 2 times the square root of n to the 2/3. All right. What is n divided by n to the 2/3? N to the 1/3. And what's the square root of n to the 2/3?
And to the 1/3.
N to the 1/3. So it's n to the 1/3 plus 2 times n to the 1/3 is 3 n to the 1/3. This is not a proof that this is the best you can do. I would really want to use calculus to attack this.
Is it gonna be like the other one where it's like close to the best, but not quite the best?
It will be close, yes. And so what we should do here is we should say x equals t n to the 1/3. We now think that maybe x is around n to the 1/3. Let's try games like that. Let's use some calculus. Let's use some plotting. And so I'm going to end with the following. So number of eggs, x for the drop, and then the cost. Gather data. When there's one egg, what is the x for the drops? We drop it every floor from the bottom up. So x equals 1. And the total cost is n. When there are 2 eggs, we drop it at?
Or we cut it.
No, we did better than that.
Oh, the square
root. So it was n to the 1/2, and the cost was basically on the order of n to the 1/2. I'm not worrying about the constant in front of n. Okay? I'm just recapping what we've done.
Those are number of eggs per power.
So let's see. When we have 3 eggs, we dropped it at n to the 2/3, and the order is n to the 1/3. So is this giving you a pattern? What do you think the cost is going to be for k eggs?
Or is it into the?
Well, how can I write n? Well, how should I rewrite n? I have n to the 1/2, n to the 1/3, 1/1. Right, this is the algebra. This is multiplying by 1. And so if I look at that 1/1, 1/2, 1/3, it makes sense that I would guess we can probably get n to the 1/k.
Yeah.
How about over here? I've got n to the 1/2, n to the 2/3. How should I rewrite the 1 over here?
And to the 0 over 1?
Yeah, why not write it as n to the 0/1, n to the 1/2, n to the 2/3? What do you think it would be over here?
And to the k minus 1 over k.
Yeah. And your conjecture is correct. But again, it's the power of seeing a pattern. We do a couple of cases by brute force, get some intuition, and now we have a conjecture that we can make. A lot of it is trying to figure out, how do I write things in a good way?
I feel like the convention of like not writing ones when they're obvious is something that like when you get to higher math, you're like, oh wait, the ones help you see a pattern.
So in physics, they talk about the rationalized MKS units where the speed of light is 1 and the gravitational constant is 1. And as a mathematician, these are terrific units to look at. But as somebody with physics background, I can't look at the equations and see the physics anymore. It's now hidden. It's much better to have that stuff there. There is a danger of simplifying things too much and you end up missing the patterns. And so here, it's much better to write it like this. And you can see now the patterns emerging. Even if you can't prove that this is the best, you can now say, hey, if you know what proofs by induction are, you could actually prove by induction that if you drop it here, that's what you'll get for the cost. So this is a good problem to end right before you go and choose what to eat for lunch. But it covers a lot of great stuff here in terms of doing algebra. We're not using calculus. We're not solving this using any complicated mathematics. This is stuff you can do. We're plotting functions, and we're trying to figure out where's the function smallest. Now, we don't want to plot it for every possible number of floors. So we figure out what's the right scale for the behavior. We renormalize, we change variables, and now we have just one function we need to plot to understand. We have two competing strategies when we talk about the trade-offs between the two. Okay, so this is a good place to stop. So let me just stop recording.